All right, we want to talk about Dalton's law of partial pressures. Dalton's law just states that the pressure exerted by a mixture of gases within the same container are the sum of the partial pressures. That is, the partial pressure is the pressure that gas was exerted had it been in the container by itself. So the total pressure is equal to pressure A of gas A, pressure of gas B, plus pressure of gas C, so on and so forth, or however many gases you have in the container. So if we look at an example, we got hydrogen and oxygen gas, both at the same volume and the same temperature. And if you push them all into one container of the same volume at the same temperature, the pressures are therefore going to add together. So we could do this and say, all right, so we got 3 ATM. And then we're going to add to it the 2 ATM from the problem. And guess what that equals? 5 ATM. The math is not hard, but just want to make sure you have the concept that those pressures are additive as long as you're at the same volume and the same temperature. That is, you're talking about gases in the same container under the same conditions. Now, one common way that that's used is with vapor pressure. That is, if you've got a liquid in a container, that head space, that space of air or even a vacuum above the surface of a liquid will contain gas phase of the liquid in question, mostly for our level, of course, water. But say we have this container, it's got liquid water, in that head space, you're going to have some gaseous water. If you were to evacuate that and allow it to evaporate until the pressure equalized, that pressure at a given temperature is the vapor pressure. Vapor pressure is temperature dependent, so you're going to have to look that up or it will have to be provided. There's an appendix in your textbook that does have vapor pressures of water. So let's look at a particular example. We got a sample of hydrogen gas collected by displacement of water at 25 degrees Celsius, and the atmospheric pressure was 748 torr. We want to know what pressure would the dry hydrogen exert in the same container. That means I'm going to need to look up the vapor pressure of the water at 25 degrees Celsius and then essentially subtract to get the pressure. If you collect it and then you have to work with it in terms of a gas law calculation, you're going to do this calculation first and then plug into the gas law calculation. So if we look that up, we find that the vapor pressure of water at 25 degrees Celsius is 23.8 torr. Subtract that from the 748 and you get 724 torr, and that would be the pressure of the dry gas in the container. So now if you have a mixture of non-reacting gases in the container, then what you find is that the partial pressure then would be equal to what we call the mole fraction times the total pressure, where the mole fraction is the number of moles of that particular gas divided by the total number of moles of all the gases in the container. Practically speaking, when we're talking about gas phase things, it's usually useful to use the pressures to get the mole fraction instead of the moles, because the pressures will be more easily measured. So we will know the mole fractions of nitrogen, oxygen, air when their partial pressures are 160 torr for the oxygen and 600 torr for the nitrogen. So this is essentially atmospheric concentration, but I just rounded off a little bit and just made it purely nitrogen and oxygen atmosphere. But let's work through that. So now if we look at this problem, we have these two gases. To get the mole fraction, I'll first need the total pressure. So that's going to be 160 torr. And I'm going to treat this to good to the ones place for 3 sig figs. And so we're going to have 600 torr for a total of 760 torr, or 1 atm of pressure. So then the mole fraction, which is that Greek letter chi, but it kind of looks like a sort of scripted X, of the O2 is going to be 160 torr divided by 760 torr, and that's going to be 0.211. You can either subtract that from 1 or do the next calculation, which is what I'll do to emphasize what we're doing. But they should always add up to 1. Notice the torr cancel, and I don't get any units. So we're going to say 600 torr divided by 760 torr, and that's going to be 0.789. Notice they do add it to be 1, but again, no units on any of the mole fractions. Let's look at another example. Let's say the mole fraction is what it was in the previous problem, 0.211, but if the air pressure were only 250 torr, what's the partial pressure of the O2 gas? So if we look at this problem, we're just going to plug in the information we're given. The partial pressure of O2 is going to equal that mole fraction, 0.211, no units, times the 250 torr. We treat that like it's got 3 sig figs. Pressure of the O2 is 52.8 torr. Okay, here's a problem where we put all of our work we've been doing together. We got a sample collected by displacement of water. That is, the gas is trapped above the water, so we are going to have to consider the vapor pressure of the water. The oxygen that was collected was 742 milliliters at 27 degrees Celsius. 27 degrees Celsius is 300 Kelvin. The barometric pressure was 753 torr. We want to know the volume of the dry oxygen STP. This is very similar to a problem we worked before, except we have to account for the vapor pressure of the water. Okay, so let's look at this. We transferred the information from the previous page. I looked up the vapor pressure of the water, and at 27 degrees Celsius, it's 26.7 torr. We're going to subtract both of those, and we'll call that 726 torr. This is the pressure that I'm going to plug in, the pressure of the gas, ignoring any vapor pressure for the water. And then remember our STP conditions. The pressure is 1 atm, or 760 torr, and the volume is what we're trying to find. The temperature is going to be 273 kelvins. So again, we're going to solve for V2. So V2 is going to be P1 V1 over T2. We're going to divide by P2 and multiply. Sorry, that should be 1, and this should be 2. And then we're going to solve it up like last time. V1 equals P1 divided by P2 times T2 divided by T1. We're going to plug and chug. 742 milliliters times our P1 is going to ultimately be that 726 torr divided by 760 torr. So that's going to cancel. That's going to be T2, so 273 Kelvin on the top, 300 Kelvin on the bottom, and the kelvins are going to cancel. So when you run that all through your calculator, you're going to get 645 milliliters, and that would be our answer.